Welcome to Science for Sleepy. Tonight, you and I step into the quiet but haunting mystery of dark matter, the ghost that seems to hold the universe together. Imagine this. Nearly everything you see, your hands, the stars above, the moon's glow, even the swirling galaxies, makes up less than 5% of the universe. The rest is not only invisible, it is untouchable. Roughly a quarter of the cosmos is dark matter, a form of matter that cannot be seen, tasted, or felt, but whose gravity shapes the heavens. The shocking part is this: if dark matter suddenly disappeared, galaxies would unravel like loose threads, stars would drift away, and the very architecture of the universe would collapse into chaos. You and I are fragile passengers on a raft made mostly of shadows. Think of it this way. You have probably spent your life believing you live in a world made of solid, ordinary things. Tables, buildings, oceans, mountains. But in truth, all of that belongs to a thin crust of reality. Underneath it, surrounding it, and weaving through it is a substance we cannot see, one that outweighs ordinary matter by more than 5 to 1. The light from distant galaxies bends around it. The stars cling to it, and yet even the most powerful telescopes cannot show it to us. The universe is lit by fireflies of visible matter, but behind them stretches a black scaffolding we only know is there, because everything else would fly apart without it. And before we drift too far into this ghostly landscape, I want to ask you something small. Could you go to the comments right now and tell us where you are watching from and what time it is there? Maybe you are listening in the middle of the night with the sound low, or perhaps in the middle of a quiet morning. We would love to know. And while you are down there, please subscribe to the channel. Think of it like dark matter itself. Your subscription is invisible, I cannot see you press it. But just like gravity, it keeps this channel from flying apart into nothingness. The strange part is how this story begins, not with glowing stars or brilliant discoveries, but with silence and confusion. In the early 20th century, scientists believed they understood most of the universe. Newton's gravity described the dance of the planets. Einstein had given us relativity to explain the bending of light and time, and telescopes had revealed billions of galaxies. It seemed like the big questions were in sight. Yet hidden beneath those confident theories was a problem so ordinary, so boring in its details, that many ignored it for decades. That problem was the speed of galaxies and the faint whisper of something unseen pulling them tight together. The first to really sense this was a Swiss astronomer named Fritz Zwicky in the 1930s. He was studying a cluster of galaxies far away in the constellation Coma. His calculations suggested that the galaxies in the cluster were moving too fast, and by all rights, they should have torn apart and scattered into empty space long ago. But they did not. They clung together as if bound by invisible glue. Zwicky, blunt and eccentric, called this missing force dunkle Materie, dark matter. His colleagues thought it was an exaggeration, or perhaps an error in his measurements. For decades, his warnings echoed quietly, ignored by the larger scientific community. It is strange to think how one man looking through a telescope in the 1930s might have glimpsed the shadow of something that now dominates our understanding of the cosmos. Imagine for a moment what it would feel like to be Zwicky, standing at the edge of a mountain observatory, peering through fragile glass lenses and realizing that the universe you thought you knew was missing most of its mass. Imagine telling your peers that the universe is mostly invisible and having them shrug, dismissing you as dramatic. How would you continue your work, knowing that you might be right, but that no one wanted to believe in something so unsettling? And this is the haunting truth that you and I must carry as we step into this journey. Everything we see is not the whole story. When you look at the night sky, you see beauty, but behind it lies something heavier, stranger, and invisible. What kind of world is it where the most important things cannot be seen at all? The story of dark matter could have stayed hidden in plain sight forever, if not for a man named Fritz Zwicky. It was the 1930s, a decade shadowed by global economic depression and political tension, and yet, in the quiet halls of astronomy, another kind of shadow was forming, an unseen presence hanging over the galaxies themselves. Zwicky, working at the California Institute of Technology, was not the kind of man who blended politely into scientific circles. He was outspoken, often abrasive, and described by some of his colleagues as brilliant but difficult. He once admitted openly that he did not mind being disliked, so long as the universe itself surrendered its secrets to him. Perhaps it was this stubborn streak that allowed him to see what others ignored. At the Palomar and Mount Wilson observatories, Zwicky turned his attention to the Coma Cluster, a massive collection of galaxies more than 300 million light-years away. Through the telescopes of the time, the galaxies appeared as faint smudges of light, each one containing billions of stars. They looked quiet, almost frozen in space, but when Zwicky measured their motions, he found something troubling. These galaxies were racing around at incredible speeds, far faster than the visible matter could explain. By the laws of Newton and Einstein, the cluster should have disintegrated, the galaxies flung apart into emptiness. Yet they remained together, held in place as if by an invisible hand. Zwicky did what any careful scientist would do. He ran the numbers again. He calculated the total mass of visible stars and compared it to the gravitational pull required to keep the cluster intact. The difference was staggering. He concluded that the cluster must contain far more matter than what was visible, perhaps hundreds of times more. He gave this missing mass a blunt name, dunkle materie, or dark matter. In truth, the way Zwicky presented his idea was both the strength and the weakness of his discovery. He spoke directly, even harshly, and his colleagues often bristled at his manner. One of his contemporaries joked that Zwicky had discovered not just dark matter, but also a new kind of social repulsion. But beneath the barbed personality was a mind working ahead of its time. The invisible weight he described was not a small detail to be corrected. It was a glimpse into the true nature of the universe. Yet the 1930s were not ready for this idea. Physics was in a golden age, buzzing with the discoveries of quantum mechanics, relativity, and the growing understanding of nuclear forces. The excitement was in particles and equations, not in the dull business of weighing galaxies. To most, Zwicky's claims seemed unremarkable, or perhaps even careless. Was it not more likely that he had miscalculated, that his instruments were imprecise, that the galaxies were simply misunderstood? So his findings were politely noted, then quietly set aside. This neglect is one of the most haunting aspects of scientific history, the way great truths can slip past, muffled not by lack of evidence, but by lack of interest. Zwicky was not the first to be ignored. Centuries earlier, Copernicus had placed the sun at the center of the solar system, and for years his work was overlooked. In the 1860s, Gregor Mendel discovered the laws of genetics through his pea plant experiments, only to have his papers buried in obscurity until decades later. Zwicky joined their company, a man staring at a truth too large and too uncomfortable for his age to handle. But Zwicky did not stop at dark matter. His restless mind leapt across topics. He predicted the existence of neutron stars, dense remnants of supernova explosions, long before they were observed. He studied the violent outbursts of galaxies and coined the term supernova. He imagined gravitational lenses, where massive objects could bend light and magnify distant galaxies, an idea that decades later became a central tool in cosmology. Yet for all his insights, he was still remembered as abrasive, his ideas treated with suspicion. Imagine the isolation of his position. You are a scientist in the 1930s, standing at a chalkboard filled with equations, pointing at galaxies that should not stay together, insisting on a universe made mostly of invisible matter. Around you, colleagues are excited by the splitting of atoms and the rise of nuclear physics. They look at you with polite dismissal, murmuring that perhaps you miscalculated. How do you persist, knowing that the evidence is there but that no one wants to listen? It is as if you are shouting into a void, and the void is staring back at you with silence. Part of the difficulty was the nature of the claim itself. To say the universe is mostly invisible is not only shocking, it feels almost absurd. People trust their eyes, their telescopes, their instruments. If something cannot be seen, touched, or measured directly, is it real? Zwicky was essentially asking the world to believe in a shadow, and at that time, shadows did not seem as interesting as the dazzling discoveries of visible physics. Still, his work planted a seed. Though ignored, it remained in the literature, quietly waiting for someone else to return to it. In a way, Zwicky's stubbornness preserved the problem. He had pointed to something that did not fit, and science cannot rest comfortably with contradictions. Like a splinter under the skin, it stayed there, even if no one was ready to pull it out yet. It is worth pausing to think about how many great truths of history began this way, not as triumphs, but as irritations. The missing mass of galaxies was an irritation. It did not fit, it seemed dull, it lacked the glamour of nuclear breakthroughs. And yet, from such irritations, entire revolutions can grow. Could it be that many of today's overlooked problems will one day be seen as the foundations of tomorrow's greatest discoveries? There is also a human lesson in Zwicky's story. He was not loved by his colleagues, not polished in speech, not patient with dissent. But he saw what others did not, or would not. His legacy reminds us that truth does not always arrive in elegant packages. Sometimes it comes from the messy, abrasive, and uncomfortable voices. Sometimes the person who irritates you most is the one carrying the truth you need. In the years that followed, Zwicky's idea of dark matter remained like a whisper in the background. It did not vanish, but neither did it take hold. Astronomers continued to map galaxies, physicists pursued particles, and the world itself plunged into the chaos of war. The 1940s and 1950s belonged to nuclear power and rockets, not to invisible matter. Yet the universe remained patient. The galaxies kept spinning too fast. The clusters remained bound when they should not have. Reality itself waited quietly for the day someone would finally take notice again. And so, as you listen now, consider the strangeness of this turning point. A man in the 1930s looked up at a cluster of galaxies and saw something missing. He gave it a name, dark matter, and then the world turned away. For decades, the greatest secret of the cosmos sat ignored, gathering dust in the corners of astronomical reports. It makes you wonder, how many other great truths are hiding right now in overlooked data, waiting for someone stubborn enough to insist they are real? By the time the 1970s arrived, Fritz Zwicky's warnings about invisible matter were little more than footnotes in astronomy. The world had moved on. Men had walked on the moon. Radio telescopes were stretching our vision deeper into space, and physicists were busy with particle accelerators. If anyone still remembered Zwicky's Dunkel Materie, they thought of it as one of his eccentric ideas, tucked away with his gruff temper and his habit of insulting colleagues. Yet science has a way of circling back to neglected truths, and in this case, it happened not through loud proclamations, but through the quiet, careful persistence of a woman who simply wanted to understand how galaxies move. Her name was Vera Rubin. She was born in the early 1920s, a child who loved to watch the stars wheel across the night sky. Unlike Zwicky, Rubin was not combative or harsh. She was soft-spoken, meticulous, and deeply curious. At a time when women were often discouraged from pursuing science, she carried her passion with quiet determination. She earned her doctorate in astronomy and began what might have seemed like a modest career, measuring how stars rotate around galaxies. It was the sort of work many would have called routine, even dull. But sometimes the dullest measurements conceal the deepest secrets. Rubin's focus was simple. Galaxies are made of billions of stars, and those stars orbit around the galactic center. According to Newton's laws, the farther a star is from the center, the slower it should orbit. Much like planets in our solar system, Mercury whips quickly around the Sun, while Neptune drifts slowly along the edge. Astronomers expected galaxies to behave the same way, fast in the middle, slower at the edges. But when Rubin and her collaborator Kent Ford measured the speeds of stars across spiral galaxies, they found something astonishing. The stars on the outer edges were not slowing down. They were racing just as fast as the stars closer to the center. By all logic, those outer stars should have flown off into the void, flung away by centrifugal force, leaving galaxies shredded and scattered. But they did not. Instead, the galaxies held together in defiance of the laws of visible matter. The only explanation was that something unseen, some vast halo of invisible mass, was wrapping around the galaxies and binding them together. Rubin's results were not a single fluke. She repeated her measurements across galaxy after galaxy, patient and thorough, her data piling up until the evidence became undeniable. Wherever she looked, the pattern was the same. Galaxies were spinning too fast to be explained by visible matter alone. The missing mass that Zwicky had grumbled about decades earlier now stood revealed in clean, consistent numbers. What makes Rubin's story remarkable is not just the discovery itself, but the way she embodied persistence. She was not chasing fame, not hurling accusations, not demanding to be heard. She simply kept measuring, kept charting, kept collecting data until the truth could no longer be ignored. In the quiet hum of observatories, late at night, surrounded by stacks of photographic plates and calculations, she did the work that finally convinced astronomy that dark matter was real. Imagine the atmosphere of those nights. The telescope sweeping slowly across the sky, stars flickering on glass plates, the meticulous process of turning faint light into data points. Hour after hour, night after night, she gathered the speeds of stars, tiny marks that by themselves looked meaningless, but when assembled revealed a cosmic imbalance. It was not dramatic in the moment. There were no explosions of insight, no flashes of brilliance, just slow, steady accumulation, like drops of water filling a jar. And yet, in those drops lay the weight of an unseen universe. Rubin herself spoke often about the wonder of simply looking. She once said, "We are made of star stuff. We are pieces of the universe made alive." Her view of dark matter was not just mathematical but deeply human. It was as though she recognized that we live inside a mystery, and her role was not to dominate it but to patiently listen. That patience became the force that turned Zwicky's eccentric claim into a central pillar of modern cosmology. It is worth pausing to appreciate the contrast between Zwicky and Rubin. One shouted at the world, abrasive and frustrated, while the other whispered with data, calm and steady. Both were necessary. Zwicky's fire gave the problem a name, while Rubin's patience gave it proof. Together, though separated by decades, they forced humanity to confront the idea that most of the universe is invisible. But think of what this means for you, listening now. Every spiral galaxy you have ever seen in a book or a photograph, those graceful swirls of light, are not what they seem. The glowing arms are only the visible part, clinging tightly to an invisible halo of dark matter that stretches far beyond what your eyes can see. If you could somehow strip away the stars, the gas, the dust, what would remain would be an enormous cocoon of unseen mass, silent and untouchable, yet heavier and more important than the galaxy itself. You live in a universe where the most important structures are invisible scaffolds, holding together the stage on which light itself performs. The 1970s marked a quiet turning point. Before Rubin, dark matter was speculation. After her, it became unavoidable. Scientists could no longer dismiss it as Zwicky's exaggeration. The galaxies themselves testified to its presence. Her rotation curves, the flat, defiant lines of star speeds plotted across galaxies, became icons of astronomy, haunting reminders that the universe does not follow the script of visible matter. Still, even with Rubin's evidence, the mystery deepened rather than resolved. What exactly was dark matter? What was it made of? Why could it not be seen? Rubin had revealed the weight of the ghost, but its substance remained unknown. In this sense, her discovery was both an answer and a question. It confirmed Zwicky's claim, but it also opened a new abyss of uncertainty. And perhaps this is the most haunting part. You and I live in an age where we know the universe is mostly invisible, but we do not know what that invisibility is. We see its effects, we map its gravity, we trace its outlines, but we cannot touch it, cannot catch it, cannot even explain it fully. It is as if we are prisoners watching shadows on a wall, aware that the shadows are real, but unable to step outside and see the objects casting them. So let me leave you with this thought. Vera Rubin did not set out to discover a ghost. She set out to measure stars. Her legacy reminds us that sometimes the greatest mysteries are revealed not in the extraordinary, but in the ordinary, not in the fireworks, but in the slow and careful accumulation of detail. If galaxies themselves are whispering to us that they are wrapped in shadows, what else might the universe be whispering that we have not yet been patient enough to hear? By the time Vera Rubin's careful measurements had spread through the astronomical community, the evidence was no longer a curiosity. It was a problem that could not be ignored. Galaxies were not behaving as they should, and when science finds itself staring at contradiction, it can do nothing but follow, however reluctant the path. If you think of a galaxy, you might picture a pinwheel of stars slowly drifting in space, glowing spirals suspended in the dark. But in reality, galaxies are busy, dynamic systems. Billions of stars orbit around a central mass, like fireflies caught in a whirlpool. The motion is governed by gravity, and gravity depends on mass. The visible matter, the stars, the gas clouds, the glowing nebulae, should provide enough pull to determine how the galaxy spins. But Rubin's work showed it did not. The outer stars moved too quickly, as though clinging to an invisible anchor. To understand this, imagine tying a stone to a string and swinging it around your hand. The string keeps the stone from flying away. Now imagine that the string is too weak for the speed of the stone. It would snap, and the stone would fly off. That is what galaxies should be like if they only contained visible matter. The stars at the edges should have snapped free long ago, scattering into the emptiness of space. But they remain, bound to their galaxies as though by invisible strings of immense strength. Those strings are dark matter. And it is not just individual galaxies. Entire clusters of galaxies, like the one Fritz Zwicky studied decades earlier, show the same stubborn refusal to behave. Hundreds of galaxies spin and whirl in groups, their collective motions far too wild to be explained by the visible stars alone. Without unseen mass, the clusters should have dissolved billions of years ago. Yet here they are, ancient and intact, as though some vast unseen hand cups them gently together. One of the most startling images comes not from telescopes, but from the quiet accumulation of data. When astronomers map out the distribution of galaxies, they find that they are not scattered randomly across the universe. Instead, they form long filaments, great webs of structure stretching across unimaginable distances, with vast empty voids between them. If you could step outside the universe and look down upon it, the galaxies would look like dewdrops strung along invisible threads. Those threads are not made of light or gas. They are made of dark matter, forming a cosmic scaffolding upon which everything else clings. You might be tempted to think of dark matter as exotic, mysterious particles, but at this stage, astronomers were not concerned with its identity. They only knew its presence was required. It was like balancing an equation and finding something missing on one side. The missing piece had to be there, or nothing else made sense. It was not speculation anymore, it was necessity. And yet, the unsettling part is how invisible it remains. You and I can see galaxies through telescopes. We can trace their light across billions of years. But dark matter emits no light, no radiation, no signal that our instruments can directly detect. It is like standing in a room where the furniture is covered in sheets. You see the outlines only because of the way the sheets sag and fold. You never glimpse the thing itself, only its effect. Imagine driving on a dark road at night and suddenly feeling your car pulled to one side. You cannot see what caused it, but the skid marks on the pavement tell you something heavy and invisible was there. That is what dark matter is to the cosmos. An unseen force whose presence is betrayed only by the way it tugs on everything else. The irony is that most of the universe's story is written by this invisible hand. Without it, the galaxies would not hold together, the clusters would not exist, and the great cosmic web would not form. Even the very stars that make up our Milky Way are gathered within a halo of dark matter. You live in a galaxy balanced precariously within a cocoon of shadows. Every star you see on a clear night sky is only there because an invisible halo holds it steady. Astronomers sometimes describe dark matter as the glue of the cosmos, but perhaps glue is too tame a word. It is more like the skeleton of the universe, the hidden bones upon which all the visible flesh hangs. Without it, the universe would collapse into a very different, unrecognizable form. And yet, for all its importance, it remains out of reach, mocking us with silence. When Rubin presented her findings, many resisted at first, as scientists often do when confronted with something that overturns assumptions. Some suggested that maybe Newton's laws break down at galactic scales, that perhaps gravity itself changes in ways we do not yet understand. Others clung to the hope that errors in measurement might explain the strange curves. But as the data piled up, galaxy after galaxy telling the same story, the denial crumbled. The only consistent explanation was that most of the mass in the universe was dark. So here we find ourselves, in a cosmos where the things we touch and see are only a fraction of the whole. Stars, planets, gas clouds, all the visible matter are little more than bright decorations on a much larger, invisible stage. You might walk through your day believing that reality is made of what your eyes confirm, but the truth is stranger. The visible world is only the surface. The deeper truth is hidden, silent, and vast beyond measure. And perhaps this is the most human part of the story. We are creatures of light, drawn to what we can see. We build our knowledge on the visible, the measurable, the tangible. But the universe is reminding us that light is not the whole truth. In fact, it is a small fraction. The real structure of existence lies in the darkness, and we are left to wonder if we will ever truly grasp what it is. So I leave you with this thought. If everything you know and trust, the stars, the planets, your own body, are only a fraction of reality, then what kind of universe do we truly live in? What else might be waiting, invisible but essential, shaping us without our knowing. Before we dive deeper, I need to pause with you here. If you have not subscribed yet, this is the moment. Without your invisible support, this channel will collapse. The same way galaxies would collapse without dark matter. We might look bright on the outside, but underneath there has to be something unseen holding us together. If you like wandering through mysteries like this, your subscription is the quiet gravity that lets us keep building more. So please become the hidden mass that keeps science for Sleepy alive. Now, let us turn from galaxies to the universe itself. If galaxies whisper of something unseen, the universe as a whole sings of it, and the song is ancient, older than stars, older than planets, older than life itself. It is the faint glow of the cosmic microwave background, the afterglow of the Big Bang, still washing across the universe nearly 14 billion years later. In the early 1960s, two engineers at Bell Labs, Arno Penzias and Robert Wilson, were testing a radio antenna. They expected static, but instead they heard a strange background noise. No matter where they pointed the antenna, the noise remained. They even cleaned pigeon droppings from the equipment, thinking perhaps it was interference, but the hiss did not vanish. What they had stumbled upon was the oldest light in the universe, the fading echo of creation itself. This light, stretched into microwaves by billions of years of cosmic expansion, carries with it a detailed memory of the infant universe. And like any memory, it contains subtle patterns, tiny fluctuations in temperature and density. These ripples are the fingerprints of everything that would later form: stars, galaxies, clusters. They are the seeds of structure. When satellites like Kobe in the 1990s, WMAP in the early 2000s, and Planck in the 2010s mapped the microwave background in exquisite detail, the results were astonishing. The patterns matched predictions only if dark matter was included. Without dark matter, the ripples could not grow into galaxies. Ordinary matter, made of atoms, was too hot, too energetic, and too easily scattered by radiation in the early universe. It needed the invisible scaffolding of dark matter to gather around. Like dew forming on blades of grass, ordinary matter clung to the invisible framework of dark matter, condensing into the galaxies we see today. Imagine the early universe as a vast ocean of particles and light, roiling and chaotic. Ordinary matter was like foam tossed about by waves of radiation. It could not settle into stable forms, but dark matter, indifferent to light, drifted silently, gathering into invisible wells of gravity. Into those wells, ordinary matter fell, cooled, and ignited into stars. Without dark matter, the universe might still be an endless fog, too smooth, too empty, lacking the structure needed for life to emerge. What makes the microwave background so haunting is its quietness. It is not a blazing signal. It is a faint whisper of static, detectable only with careful instruments. And yet, in that whisper, the universe tells its story. When you hear the hiss between radio stations, you are partly hearing the afterglow of the Big Bang itself. In that hiss is written the invisible presence of dark matter, shaping the cosmos before galaxies were even born. Think of how strange this is. The most powerful evidence for dark matter comes not from what we see, but from what we do not see. It comes from ripples in ancient light, from tiny variations in microwave radiation that look to the human eye like little more than colored blotches on a map. And yet, those blotches are the scaffolding of existence. They are proof that we live in a universe woven through with shadows. The history of these discoveries also reminds us how patient science must be. Penzias and Wilson found the microwave background by accident, thinking it was noise. The COBE satellite, launched in the late 80s, revealed the first rough map of the ripples. The WMAP satellite, 2 decades later, refined that picture into something more precise. And then Planck, Another decade on provided even greater detail. Decade by decade, mission by mission, we slowly assembled the story. Dark matter did not appear in a single flash of revelation. It emerged from the quiet accumulation of dull but stubborn evidence. And here is the deeper thought to hold as you drift. You and I, every person alive, exist because of those ripples. If the early universe had been perfectly smooth, with no variations, nothing would have formed. No galaxies, no stars, no planets, no life. The unevenness, magnified by dark matter's invisible pull, created everything we know. Our very existence is tied to the ghostly scaffolding that shaped the first sparks of structure. So let me ask you this as you close your eyes and imagine that faint microwave glow. If we are beings of light, born from stars, shaped by atoms, what does it mean that our lives are also built upon shadows? If dark matter had not been there, silently guiding, would there have been a universe at all for us to call home? After drifting with the faint afterglow of the universe, let us come back down to Earth. You might imagine the search for dark matter as a task for telescopes scanning the sky, but much of the real hunt happens underground, hidden away, where the Earth itself acts as a shield. The problem is simple in theory, but maddening in practice. If dark matter is real, then it must not only shape galaxies, it must also be here, right now, flowing through you, through me, through the room you sit in. Imagine a ghostly wind of invisible particles streaming across the Earth every second, a silent current that passes unnoticed. But if these particles exist, could we catch one? Could we hold in our hands a piece of the unseen majority of the cosmos? Physicists have given names to their quarry. WIMPs, weakly interacting massive particles, were once the favored candidate. Heavy, slow-moving, and reluctant to touch ordinary matter, WIMPs seemed to fit perfectly. Another idea was axions, particles so light and strange they almost feel like the whispers of mathematics made real. And so, around the world, detectors were built like traps for shadows, waiting for the faintest sign of a ghost brushing against ordinary matter. Some of these traps are astonishing feats of patience. In deep mines, scientists build tanks filled with liquid xenon, a noble gas cooled to freezing temperatures. The hope is that a passing dark matter particle will nudge one of the xenon atoms, creating a tiny flash of light. Sensitive instruments wait for these flashes, ready to record an event that may never come. Other experiments use crystals, chilled nearly to absolute zero, hoping to feel the faint vibration of a particle colliding with the lattice. Why go underground? Because the world above is noisy. Cosmic rays rain down constantly, showering the Earth with high-energy particles. To find something as elusive as dark matter, you must retreat into silence, deep beneath mountains where the rock absorbs the chaos of the sky. It is there, in the stillness, that detectors wait like patient hunters. The results so far have been frustrating. Year after year, experiment after experiment, the silence remains. There are hints, occasional blips, but nothing that holds up under scrutiny. Some detectors whisper of possible signals, only for others to contradict them. The ghost remains a ghost, refusing to be pinned down. And yet, the effort continues, because the alternative is to give up on understanding the invisible structure of the universe. Imagine the dedication required. Teams of scientists spending decades in frozen caverns, calibrating machines that might never succeed, waiting for a flash of light smaller than the blink of an atom. It is a strange kind of devotion, one that blends hope with monotony, patience with obsession. There is something almost poetic in this search. The detectors are designed to record silence, to notice the rarest of disturbances. Entire careers are spent building devices to capture what may never appear. And yet, this is how science moves forward, not with dramatic revelations, but with the quiet persistence of those willing to listen to nothing for years, in the hope that one day the nothing will speak. The particle search also mirrors human restlessness. We cannot seem to accept that something so vast and important could remain beyond our reach. We need to touch it, measure it, pin it down, even if that means digging into the earth itself. There is an echo here of older hunts, miners digging for gold, explorers searching for lost cities, seekers chasing myths. Dark matter may be a scientific puzzle, but it carries the same allure as any treasure hunt. And what if the treasure is not what we expect? Some theorists now suggest that perhaps dark matter is not WIMPs or axions at all. Perhaps it is something stranger, sterile neutrinos, or entirely new kinds of particles that do not even exist in our current models. Each failed experiment forces us to widen the search, to admit that the ghost may not fit into the tidy boxes we have built. It is worth pausing here to think about the scale of this search. We are talking about particles smaller than atoms, invisible to our senses, passing through everything around us without notice. And yet, to catch even one, we build machines the size of buildings, bury them under mountains, and wait for years. The disproportion feels almost absurd, giant human effort directed towards something that may not even be there. And yet, this absurdity is what makes the search beautiful. It is proof of human stubbornness, our refusal to let go of mysteries. The irony is that the absence of evidence does not weaken the case for dark matter. The galaxies still spin too fast. The universe still requires unseen mass to form the structures we observe. The cosmic microwave background still shows patterns only dark matter can explain. The ghost remains woven into the fabric of reality, whether or not we can trap it in a laboratory. So the experiments continue, like lighthouses shining into an endless night, hoping to glimpse a traveler passing by. They may fail in our lifetime, but perhaps in the lifetime of those who come after, the ghost will finally brush against the detector and the story will change. And now, as you sit with this thought, I leave you with a question. What does it mean to search for something that may never be found? Is the pursuit itself enough? Or must the ghost one day step out of the shadows to justify the decades of waiting? Science is often painted as a march toward truth, but more often it is a walk through fog, where each step reveals new shapes that might be real or might be illusions. Dark matter itself is one of those shapes, compelling, consistent, yet always just out of reach. And so, inevitably, some have asked a daring question. What if the ghost is not real at all? What if the problem lies not in matter, but in the way we describe the universe? In the 1980s, physicist Mordechai Milgram proposed something bold. Perhaps Newton's law of gravity, the very principle that guides falling apples and orbiting planets, is incomplete. He called his idea MOND, short for modified Newtonian dynamics. The idea was not that dark matter exists, but rather that gravity itself behaves differently on cosmic scales. At very low accelerations, perhaps gravity grows stronger than Newton predicted, binding galaxies together without the need for unseen mass. To many, this seemed outrageous. Newton's law, refined by Einstein's relativity, had stood for centuries. To tinker with it felt like tampering with the foundations of physics. And yet, Mond worked surprisingly well at describing the rotation curves of galaxies, the very curves that had given Vera Rubin such compelling evidence for dark matter. It was as though MOND offered a shortcut, explaining the data without invoking invisible ghosts. But science is not a place for shortcuts alone. A good idea must work not just in one corner, but across the vastness of evidence. And here, Mond began to stumble. While it described galaxies well, It struggled with larger structures like galaxy clusters. It also could not account for the ripples in the cosmic microwave background, the ancient light that spoke so clearly of dark matter's guiding hand. Still, MOND did not fade away. It was refined, reworked, and folded into more complex theories like Defies, which tried to blend it with relativity. The persistence of these efforts says something important. Even when the majority of evidence points toward dark matter, there remains a deep unease in accepting something we cannot see. Perhaps it is human stubbornness. Perhaps it is scientific caution. Perhaps it is simply the reluctance to believe that the majority of the universe is made of ghosts. There is another reason alternative theories persist. They remind us that science is not about certainty, but about testing the limits of our knowledge. By pushing against the mainstream idea, they force it to strengthen, to be tested from every angle. If dark matter survives these challenges, it will be because it has earned its place, not because it went unchallenged. Think of the Bullet Cluster, a pair of colliding galaxy clusters observed in the early 2000s. The visible matter, mostly hot gas, slammed together and slowed, while the gravitational lensing patterns showed the bulk of mass passing through untouched. To many, this was the clearest picture yet of dark matter at work, but to advocates of MOND, it was a challenge, forcing them to stretch their theory, to find explanations that grew more complicated with every new observation. This back and forth might seem frustrating, but it is the heartbeat of science. Theories are not monuments, they are living things, tested and revised, often discarded, sometimes reborn. Even if MOND and its cousins never replace dark matter, they sharpen the questions, reminding us that no idea is sacred, not even gravity itself. There is also a philosophical layer here. If dark matter is real, then we live in a universe where most of reality is hidden, unknowable to our senses. If dark matter is not real, and instead our laws of physics need rewriting, then we live in a universe that refuses to be tamed by our simplest rules. In either case, the universe is stranger than we imagined. And here, perhaps, is where the alternatives find their true value. Not in overthrowing dark matter, but in reminding us of humility. The story of science is not the story of conquering mysteries, but of learning to live with uncertainty, of asking questions that may take centuries to answer. So as you rest with this thought, let me leave you with the open door. What if dark matter is not a ghost, but simply our misunderstanding of gravity itself? If the rules we rely on every day are incomplete, what else might be waiting to surprise us in the darkness? If the search for dark matter in underground caverns is like listening for silence, then the search in the heavens is like watching shadows dance across a wall. The shadows are not the thing itself, but they reveal its presence. One of the most powerful ways we glimpse dark matter is through a phenomenon predicted by Einstein in the early 20th century, gravitational lensing. Gravity bends light. When light from a distant galaxy passes near a massive object, the path of the light curves. To us, the galaxy looks distorted, stretched, or multiplied, as if the universe itself were a lens, and the stronger the mass, the stronger the bending. By mapping these distortions, astronomers can weigh the invisible. They can draw maps of dark matter, not by seeing it directly, but by seeing how it bends the light from galaxies far behind it. What they find is unsettling. The maps do not match the distribution of stars or gas. Instead, they reveal vast halos of unseen mass, shaping galaxy clusters, guiding their dance. The visible matter is just the frosting. The real cake is something else, something dark. The most famous case of this is the Bullet Cluster, a cosmic collision over 3 billion light-years away. Two galaxy clusters slammed through one another like colliding waves. The gas, hot and luminous, slowed and piled up in the middle. But when astronomers mapped the mass using gravitational lensing, The bulk of the weight had sailed on ahead, ignoring the collision. What we saw was a split, the visible matter in one place, the gravitational mass in another. It was as though the ghosts had walked straight through the wreckage, untouched. To many scientists, the bullet cluster is the smoking gun. Modified gravity theories strain to explain it, adding layers of complexity, while dark matter fits naturally. The collision reveals that most of the mass is not in stars or gas, but in something invisible, something that does not collide, does not slow, does not shine, something that moves like a ghost through the chaos. And it is not just one cluster. Similar collisions have been observed elsewhere, reinforcing the same strange truth. The universe carries a hidden weight. Computer simulations take this further. With the power of modern supercomputers, scientists simulate the birth of the cosmos, starting with the faint ripples of the cosmic microwave background. They run the equations forward, letting gravity pull, matter clump, and structures grow. Without dark matter, the result is a dull, nearly empty universe, too smooth to match what we see. With dark matter, the simulations bloom into a cosmic web, filaments of galaxies stretched across vast voids, knots of clusters at intersections, a structure so intricate it resembles neurons in a brain. And when astronomers map the real universe, using surveys of millions of galaxies, the match is uncanny. The cosmic web of reality and the cosmic web of simulation look alike. Dark matter is the hidden scaffold on which galaxies are threaded like beads. There is a quiet beauty in this. We cannot see dark matter, but its fingerprints are everywhere. In the stretching of light, in the aftermath of collisions, in the great web of galaxies across the night. It is like watching the wind shape trees, or feeling the tug of a current beneath the surface of a calm sea. The thing itself is hidden, but its influence is undeniable. And yet, for all its power, dark matter remains unsatisfying. We can map it, weigh it, trace its effects, but we cannot hold it, cannot name it, cannot capture it in a detector. It is like a ghost whose footprints cover the floor, whose shadow falls across the wall, but who never steps into the light. Perhaps this is why the search feels almost mythic. Dark matter has become a story we tell ourselves, half proven, half imagined, held together by evidence that is overwhelming yet incomplete. We know it is there, but we do not know what it is. And so I leave you with this. If the universe is filled with shadows that bend light and build structure, are we seeing reality as it is, or only as it is distorted through the lens of our own limited vision? If most of the universe is unseen, how much of what we believe to be solid truth is only a shadow on the wall? In the present day, the hunt for dark matter has become a global enterprise, a quiet but relentless quest spanning continents and decades. The telescopes and detectors are no longer isolated instruments in small observatories. They are monumental machines, often the size of buildings, meticulously designed, coordinated across nations, and staffed by teams of scientists who have dedicated their lives to chasing the unseen. In the deserts of Chile, the Atacama Cosmology Telescope peers into the microwave sky, mapping the faint afterglow of the Big Bang with incredible precision. High above, satellites like the European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope are designed to measure the subtle distortions in light caused by dark matter's gravity. Across oceans, the Large Synoptic Survey Telescope, now called the Vera-C, Rubin Observatory, in honor of the astronomer who first confirmed dark matter's existence, will scan the night sky repeatedly, catching changes, movements, and patterns invisible to the naked eye. And beneath the Earth, in the depths of mountains and frozen caverns, instruments wait silently. Tanks of liquid xenon, cooled to near absolute zero, lie in shadowed chambers, isolated from cosmic rays and terrestrial noise. Sensors are tuned to detect the faintest flicker of energy, the smallest vibration that might betray the passage of a dark matter particle. Scientists descend into these chambers like spelunkers exploring a subterranean world, moving with careful purpose, each step measured, each action deliberate. These efforts are staggering in scale, and yet, the people behind them remain patient and persistent, often living with months or years of silence. They calibrate, troubleshoot, and rebuild instruments, sometimes repeatedly, driven not by fame, but by a quiet curiosity, a desire to know what lies beneath the visible cosmos. There is a certain humility in this work, a recognition that the universe does not yield its secrets easily. One must wait, often for decades, to catch even a hint of what is unseen. Collaboration is essential. Teams include physicists, astronomers, engineers, and computer scientists. They communicate across time zones, exchange enormous data sets, and rely on simulations to interpret the patterns they observe. The work is meticulous, sometimes repetitive, sometimes dull, but always aimed at the same elusive goal: understanding the invisible majority of the universe. Each experiment, each survey, each calibration brings them closer, or at least refines the map of what they are looking for. Even with the largest telescopes and the most sensitive detectors, the ghost remains elusive. The experiments, both terrestrial and orbital, continue to return null results for direct detection of dark matter particles. Still, every null result is a kind of knowledge, a map of where the ghost is not, refining the search, ruling out possibilities, guiding future efforts. Scientists have learned to treat these null results with respect. They are not failure, they are data, and data is the language the universe speaks. In many ways, this effort mirrors the history of exploration. Consider the great voyages of the 19th and early 20th centuries, ships venturing into icy seas, surveying unknown continents, charting maps of lands never seen before. The explorers did not always find what they expected, yet their charts, their observations, and their journals laid the groundwork for the future. Similarly, modern dark matter hunters chart the invisible, mapping the universe not by sight but by influence. There is also a human dimension that is often overlooked. These scientists work in extreme environments, remote deserts, high-altitude observatories, and underground facilities where silence can be absolute. Long hours, isolation, and meticulous repetition can be exhausting, yet the motivation persists. They are driven not by immediate reward, but by a deep-seated need to understand, to connect the visible with the invisible, to piece together the cosmic puzzle. They are patient listeners to a universe that rarely speaks plainly. Some projects, like the LUX Zeppelin experiment in the United States, involve thousands of sensors spread across enormous tanks of xenon. Teams must maintain cleanliness to avoid even the smallest contamination, because even a single radioactive particle can mimic the signal of dark matter. Others, like the European Space Agency's Euclid, require precise orbital positioning and coordination with Earth-based observatories, capturing data over years to reveal subtle distortions in distant galaxies. The scale of the effort is a testament to the stubbornness of the human spirit. And yet, for all this sophistication, the basic challenge remains the same as in Fritz Zwicky's time: how to observe the invisible. In the 1930s, he measured galaxy speeds and deduced the presence of dark matter indirectly. Today, we map distortions in light, analyze microwaves from the dawn of time, and wait in underground laboratories, hoping a particle will brush against a sensor. The tools have changed, but the principle is unchanged. The universe is whispering its secrets, and we must be patient enough to listen. Modern simulations also play a critical role. Supercomputers now model trillions of particles, tracing the growth of structure over billions of years. These simulations allow scientists to test hypotheses about dark matter, to see what kinds of particles and interactions could produce the universe we observe. When simulations match observations, the web of galaxies, the clustering of matter, the bending of light, the ghost seems to emerge from invisibility. And yet, it is always provisional, a model constrained by evidence, awaiting confirmation by direct detection. There is also a cultural dimension to this pursuit. The search for dark matter is no longer confined to a single observatory or a single nation. It is an international effort, involving collaborations across Europe, the Americas, Asia, and beyond. Teams share data, methods, and insights, recognizing that the ghost they chase is bigger than any one country or individual. In this sense, dark matter is not only a cosmic phenomenon, it is a unifying endeavor, a challenge that binds humanity across borders. Despite the scale and sophistication, the human element remains central. Scientists tell stories of long nights at observatories, of waiting for the quiet signals, of the exhilaration when a detector registers an unusual flash. They speak of the thrill of discovery tempered by the reality that confirmation may take years or decades. There is a deep patience here, a recognition that the universe operates on its own schedule, not ours. And perhaps that is the most profound lesson. Dark matter is not only a scientific challenge, it is a reminder of humility. We are beings of light, living in a cosmos where most of the mass is hidden. We have built machines, charts, and simulations to understand it, yet the ghost remains elusive. In pursuing it, we confront our own limits, and we learn the value of patience, collaboration, and persistence. So, as you imagine these enormous machines, the satellites in orbit, the underground detectors, the teams of scientists working quietly and carefully, think about what it means to dedicate decades to chasing what cannot be seen. The universe has not yet revealed its full hand, and perhaps it never will. And yet, the search continues, because even the faintest whisper of understanding is worth decades of patient listening. And so I leave you with this thought. If entire generations of human effort can be devoted to understanding something invisible, what does that say about the way we perceive reality? How much of the universe is always beyond our grasp, shaping everything we know, while remaining forever unseen? As we arrive at the edge of our journey through dark matter, it is worth stepping back, letting the mind wander across the vast invisible structures that shape the cosmos. From Fritz Zwicky's footnotes in the 1930s to Vera Rubin's meticulous observations decades later, from underground detectors to orbiting satellites, the story of dark matter is not only a tale of science, it is a tale of humanity itself, our desire to understand, and the humility we must accept in doing so. Dark matter is everywhere, yet nowhere. It fills galaxies, stretches across cosmic filaments, and wraps clusters in invisible halos. Without it, the universe would look entirely different. Galaxies would have long since dispersed, stars would drift apart, and the vast cosmic web, the skeleton on which all matter hangs, would not exist. You and I live in a universe held together largely by something that cannot be seen, cannot be touched, and cannot be captured. It is both intimate and overwhelming, a reminder of the scales and forces that shape us, even as we remain largely oblivious. Consider the philosophical implications. Every star in the night sky, every planet orbiting those stars, every atom in your body owes its place in the cosmos to the gravitational pull of unseen mass. We are, in a sense, the children of ghosts, formed and guided by entities that defy perception. The universe we take for granted, bright and vibrant with light, is only a fraction of what truly exists. Most of it is dark, hidden, and silent, shaping reality in ways we struggle to grasp. This perspective reshapes our sense of scale and importance. Humans are creatures of light and matter, but the majority of the universe is neither. Dark matter is the hidden majority, indifferent to our existence, yet without it, our existence would be impossible. There is a strange humility in realizing that everything we perceive, everything we touch, everything we measure, is built upon a foundation we cannot see. And yet, despite this invisibility, dark matter is knowable. Not directly, not by the senses, but through its effects, through careful measurement, through patient observation and persistent inquiry. It is a universe teaching us that reality is often stranger than our perception, that the largest and most essential parts of existence can remain hidden, even as they shape everything we experience. The story of dark matter is also a story of human curiosity and perseverance. Scientists have pursued it across decades, continents, and instruments. They have built enormous telescopes and hidden detectors, launched satellites into orbit, and written countless simulations, all in pursuit of understanding. They have followed subtle hints, mapped invisible mass, and refined theories with patience rivaling the age of the stars. Their work is a testament to the human spirit, a quiet devotion to knowing the universe even when it offers no immediate reward. And yet, even with all this effort, the ghost remains. We have measured its weight, traced its influence, and simulated its behavior, but we do not know its nature. We cannot say with certainty what dark matter is made of, whether it consists of particles, fields, or something beyond our current understanding. It may remain, perhaps forever, a mystery, a presence that shapes the cosmos yet refuses to be seen. This unresolved nature is both frustrating and beautiful. Frustrating because the answer is always just out of reach, teasing our instruments and theories. Beautiful because it reminds us that the universe is vast, complex, and full of wonders beyond our imagination. Dark matter is a silent teacher, showing us the limits of perception and the depths of curiosity, inviting us to keep looking, to keep measuring, to keep imagining. And as you reflect on this, think about the contrast between the visible and the invisible. Stars burn and shine, planets orbit, and galaxies spiral, all illuminated for our eyes to see. Yet these bright objects are only the surface, tiny fragments of the full story. The unseen dark matter is the majority, shaping everything from behind the curtain, a silent stage manager orchestrating the cosmic dance. Perhaps there is a lesson here that extends beyond science. Dark matter teaches patience, humility, and wonder. It teaches that what matters most is not always obvious, that influence can be invisible, and that the unseen can hold more power than the visible. It teaches us to value careful observation, quiet persistence, and the courage to follow evidence, even when the path is uncertain. And so, as we conclude this journey, you are left with a thought that is both simple and profound. The universe you inhabit is largely invisible. Its structure, its mass, its very coherence depends on a substance you cannot see. You live inside it, yet it surrounds you, silent, immense, and eternal. We have measured it, traced it, and modeled it, but we have not touched it. We know its presence, yet we do not know its essence. And that is the final wonder of dark matter. Not just that it exists, or that it shapes galaxies, or that it whispers through the cosmic microwave background. The wonder is that we, creatures of light and matter, can perceive its effects, can measure its influence, can even imagine its nature without ever fully grasping it. The universe remains stranger, deeper, and more mysterious than anything we have yet learned. So I leave you with this unresolved thought. If the majority of the universe is invisible, shaping everything silently and silently influencing our existence, what else might be hidden? What other forces, other forms, other mysteries surround us, waiting for patience, curiosity, and courage to bring them into the light? And perhaps, like dark matter, some of these mysteries will always remain just beyond reach, shaping our reality in ways we can only begin to imagine.